reservoirs. On behalf of SP UDESC Student Chapter, we would like to thank you, Dr. Lamas, for your participating and collaborating with us. Now you hold the lecture.
Thank you very much, Rafaela. Thank you very much, SP, for the invitation. I'm very happy to introduce to you all to Mojdeh Delshad, of who I am honored to be a former student. Dr. Delshad is a research professor at the Petroleum and Geosystems Engineering Department at the University of Texas at Austin. She obtained her master and PhD degrees from petroleum engineering at the same department. In the last 30 years, she has been involved in research on reservoir simulation, enhanced oil recovery methods, and modeling naturally fractured reservoirs. She co-founded Ultimate EOR LLC Services and later became president CEO of the company between the years of 2013 and 2019. Her current research interests include geological storage of CO2 and hydrogen. Dr. Delshad, thank you very much for accepting our invitation, and please, the word is yours.
Thank you so much, Luis. It's my honor to be participating in this event. I'm very excited about it. I had a hard time to put the picture from your flyer because it's offshore, and then I'm going to talk about onshore EOR. So, just...
Sorry for that.
No, that's okay. That's all right. I just want to make sure that it's clear that we're going to talk about onshore EOR technologies, not offshore, even though the picture is offshore. I'm excited about this event, and I'm going to share with you some of the experiences I've had with different enhanced oil recovery technologies. And then during this talk, because of the time, I'm going to focus maybe on one or two more than the other processes. And I don't know how the question-answer session is going to be. If there is a way that you can ask questions during my presentation, that would be fine. Otherwise, we keep the questions and comments to the end of the presentation.
It's up to you, actually, but usually we leave the questions for the end of presentation.
Okay, all right, I'm fine with that.
Okay.
So just starting with some statistics on the total oil reserve globally. And here I'm excluding the shale and tight oil. So we're talking about more of a conventional reservoirs, but unconventional with respect to the oil in terms of the API. So we have about 9 to 13 trillion barrels of conventional oil reserve. And out of that, about 30% is conventional oil, 15% heavy oil. In some literature, heavy oil and extra heavy oil and bitumen is considered unconventional oil. So we have 15% heavy oil, we have 25% extra heavy oil, and about 30% oil sands and bitumen. So we're talking about huge amount of oil that we can target with different technologies. So why do we need EOR? And this is a really nice picture of demonstrating that why we leave so much oil behind during the primary and secondary recoveries during the life of the reservoir. So if you look at this picture, the red is basically assuming that you have oil, the reservoir that is 100% oil saturation. So red is oil. And the ideal case is if you inject, for example, water, is shown with the blue color here, ideal case is going to be that you're going to displace all the oil in the area that you're injecting the water, and you have a very nice piston-like displacement between the water and oil. But in reality, even if you have a piston-like displacement, you're still going to leave some oil as a residual or trapped oil, even in the swept area that water has targeted. So you will leave some residual oil. It might be up to 30-35%. If the oil is more viscous, it might be 40% of the oil that you're going to leave behind. You may also have issues with the viscosity of the oil. So when you're injecting water, it's a very unfavorable viscosity contrast. So you have a fluid that has much lower viscosity than the in situ oil. So you start forming this sort of fingers or channels that is very inefficient in terms of displacing the viscous oil. On top of that, reservoirs, they're not homogeneous. So you have reservoir heterogeneity. For example, here I'm showing this in a simple case of layering, that you have like high permeability layer here, a low permeability layer there, and then the fluid is going to move according to the permeability. So you have very inefficient displacement front. There are places that you have a lot of water is going, and there are places in the reservoir that you have very little water that is displacing the oil. So that makes it very inefficient in terms of the process and recovery factor. And then the most extreme case in complexity is when you have reservoir that you have natural fractures. So these are naturally fractured reservoirs. And if the matrix is oil wet, so the wettability of the matrix rock is oil wet or mixed wet, then whatever you inject, gas or water, is just going to go through the fracture network, and you're not going to have much of production from the matrix. So these are some of the reasons that we leave so much oil behind during primary and secondary recoveries, and that's why we need improved technologies. So enhanced oil recovery, EOR, we're referring to methods that recover oil that you left behind after primary production or secondary floods. So whatever oil that you leave behind, we want to produce them with these EOR methods. And the reason you do these EOR techniques, they're actually trying to improve the sweep efficiency by injecting some materials that they're not normally present in the reservoir. And they can help you with reducing remaining oil saturation. So for example, when you're injecting CO2, in general, not all the reservoirs, they have CO2 in situ. Or when you inject polymer, you don't have reservoirs that they have polymer. So these are new materials that you're injecting, trying to produce the remaining oil. And your remaining oil, actually, there are two targets. One is the residual oil that you leave behind in the swept area. So this is the white area here that has been swept by water, for example, and you still have some residual oil here. So that would be one target for EOR in terms of the oil saturation. The other oil is the oil that was not flooded by the water flood, for example, and that is called bypassed oil. So these are the areas that the water didn't touch during the water flood, and you're going to have significant amount of oil remaining in these bypassed or unswept areas. So then I like to classify the EOR methods based on the fluid that you're injecting. So we have gas-based EOR. So in every one of these projects, you need to inject gas. And that gas can be CO2, which might be miscible or immiscible with the oil, air, hydrocarbon, nitrogen. And there are a lot of times we just don't inject the gas by themselves. We do some sort of water alternating gas, or we may add foam to help with the mobility control and improving the sweep efficiency. So a lot of times water alternating gas and foam helps with the efficiency of the gas projects. Then we have water-based EOR methods. For example, low salinity water flood or smart water flooding. If you add polymer to the water, it becomes polymer flood. If you add surfactant, the surfactant flood, or alkali like sodium carbonate or sodium hydroxide. And of course, you can combine these chemical methods. For example, it can be a surfactant polymer or alkali surfactant polymer. You can use a polymer gel, so a lot of methods for profile control or conformance control to help with the reservoir heterogeneity. They're the same polymers that we use for EOR, but then you may have a cross-linker that forms a gel with a more severe viscosity, contrast, or permeability reduction. We also have microbial enhanced oil recovery, and there are some projects, especially offshore, that they're seriously looking at microbial enhanced oil recovery methods. And really the benefit of microbial is you may have some byproducts of surfactant and polymer with the bacteria and nutrients that you provide, and sometimes they also can cause permeability reduction due to the growth of bacteria in situ. For heavier oil, we have thermal methods, including steam flooding, steam-assisted gravity drainage, SAGD, cycling steam stimulation, this is like huff and puff, and then in situ combustion, sometimes we refer to it as high-pressure air injection. So you're injecting air which contains oxygen at very high pressure, and then you create a combustion in situ. So why do we need to do EOR? Because first of all, you already have the reservoir. You found the reservoir, is a known reservoir. You don't need to find them. You already have some infrastructure in place, like for example, during your primary production, you have all the wells in place, and then you switch to water flood. You have all of your facility for water flood in terms of the separation, in terms of the wells, and so on. So you already have some infrastructure. It's not as expensive as developing a greenfield. And you already have knowledge about subsurface. So when you do primary production, when you do water injection or gas injection in a secondary mode, you understand more about the subsurface in terms of the heterogeneity and be able to optimize it further for the EOR methods that are relatively more expensive than water flood. And all of these technologies, they're mature. Any of the EOR methods that you look at, they've been around for a long time. So these are really mature technologies, and they can be cost effective, of course, depending on the process and depending on the price of oil. So about 65%, that's really the key. About 65% of the oil still remains after secondary recovery. After primary and secondary, on average, you may leave still 65% of the oil behind. So that's significant amount of oil that can be a good target for EOR. So once again, let's just review the EOR methods typically used for onshore, but some of them, they can actually apply to offshore. And if you like to know, maybe during the QA, we can discuss that. So a low salinity water flood, polymer, surfactant polymer, alkali surfactant polymer, alkali co-solvent polymer. So these are some of the chemical methods that have been used in a lot of field cases. Also, when you add foam for mobility control of gas or also mobility control with surfactant, they're considered as chemical EOR methods. Polymer gel and microbial. Then for gas injection, again, we can have miscible or immiscible gases, and there are a lot of options to select gas, and I will talk about that pretty soon. And then we have thermal and non-thermal methods for heavy oil. Sometimes you don't need to use steam, for example, to produce the viscous oil. And what is new is really this hybrid EOR, when you mix different technologies. And that's what has been happening with a lot of EOR methods in the last decade or so. For example, combining low salinity water flood with polymer. So rather than using, for example, seawater or very high salinity water for polymer flood, you may be able to reduce the salinity, and there are a lot of benefits in terms of cost and in terms of the recovery factor when you combine the two processes. You can also do low salinity CO2. And there are groups that they've been looking at low salinity CO2. There might be some benefits there as well. You can combine gas flood with surfactant flood, and is really is not a foam, but you generate in situ foam, but is really you're doing a low tension surfactant flooding plus a gas flooding. And that gas can be miscible, it can be immiscible, it can be nitrogen or CO2. So you have quite a bit of flexibility. And this is the area that a lot of companies and universities, they've been focusing on to improve the efficiency of both gas and surfactant floods. You can do steam with solvents. So what has been happening with thermal methods is just how to improve the efficiency of the steam floods, not to use as much water, for example, and not, therefore not to use as much steam. So a lot of variations of steam flood have been looked at for optimization, and they're considered as hybrid methods. Now, I like to classify the EOR for two different types of oil: light oil and heavy oil. So for light oil, you have gas floods. You can do gas huff and puff if you have issues with the reservoir properties. Polymer flood, surfactant polymer, foam or low tension foam, alkali surfactant polymer, alkali co-solvent polymer. So instead of using surfactant, you're just going to use a cheaper product, a co-solvent. And doing wettability alteration. For example, if you have carbonate reservoir and the process is not very efficient, being mixed wet or oil wet, you can use chemicals, the same chemicals that we use here, to modify the wettability, and then you benefit from the wettability alteration. Low salinity water and gel, which are a lot of different variations of gel, like preformed particle gels, bright water, and colloidal dispersion gel. These are more recent technologies on polymer gel. And the ones that I have in orange colors, they're actually chemical methods. So you see there are quite a bit of chemical methods that they can apply to a light oil EOR. And then on the heavy oil, a lot of processes include some sort of heat. So we have CSS, SAGD, vapor extraction, and a lot of variation of steam drive. For example, adding solvent, adding CO2 or other gases, so you minimize the amount of steam that you need to generate. And then we have chop, that you don't need to use any sort of energy. All you're doing, you're producing the heavy oil with sand, and it's called cold flow. And there are a lot of projects, for example, in Venezuela, and I believe also in Venezuela. If the reservoir is not favorable for steam injection, for example, is too deep, or maybe the properties of the crude oil is not favorable for steam injection, then you can do in situ combustion or high pressure air. So you in situ, you generate the steam and hot water to reduce the viscosity of the heavy oil. And I'm sure you've seen now that the heavy oil recovery extends to chemical floods. A lot of successful projects in Canada and other places for polymer flood. Alkali surfactant polymer is very popular also for heavy oil. Alkali co-solvent polymer and alkali polymer. So again, you see now there are some chemical methods that you can use for heavy oil. So the conclusion is the chemical EOR methods, they work for both light and heavy oil. And that's actually one of the favorable attribute of chemical EOR methods. So a little bit of screening guidelines for EOR. And just to refresh your memory, the API gravity is defined as this constant 141.5 divided by specific gravity, which is the relative density of the oil to the water, minus this constant 131.5. So for example, if you have a specific gravity of 1, so the oil and water densities are the same, then you get API of 10. And that is considered heavy oil. And most of the time, you're going to screen that as your first option for a thermal method. For the API of 12 is also considered heavy oil and is good for thermal methods as well. When you get to the API of 19, you can do either thermal or maybe looking at alkali surfactant polymer, alkali co-solvent polymer, or alkali polymer. So alkali becomes a good option also when you get to this level of API of the oil. API of 29, that's the lightest oil that you can consider for alkali flooding. And normally you don't use that also for steam or thermal methods. When you get to the range of 30 to 40 API oil, this is a medium gravity oil, and surfactant polymer, CO2, hydrocarbon miscible floods, they're really good for this range of API. So just based on the API of the crude oil, you can, very high level, you can decide which EOR method might be preferred. So just showing you some examples of API.
We are having some technical issues. Dr. Delshad is still there.
What's happening? Hello?
Everything all right? I can hear.
You can hear me?
Yes, can you hear her, Professor Lamas?
I haven't changed anything, so I'm
yeah, sure. Me neither. I think it's everything is okay.
Everyone back?
Mm-hmm.
Okay.
Are we okay?
Yeah.
Okay. So this is an example of showing the average reservoir depth in feet as a function of the API of the crude oil for different processes, the actual projects. And of course, you see that when you have low API, mainly there are steam floods. And then when you get to higher APIs, you see a lot of CO2 floods. And then for the range of, still higher APIs, you may have different gases like, hydrocarbon or nitrogen gas that go from a lower API to a higher API because not necessarily they've been miscible with the oil. And then chemical also can be over a wide range of APIs. So you see some projects with circle that they are chemical EOR method. So again, API of crude oil can be a very good way of screening. And of course, also here you see that the shallower reservoirs, they're good for steam flood. For CO2, you need, moderate depth not too shallow, not too deep. For other gases, you may have to be much deeper. For example, if you want to do miscible nitrogen, then you really need to go very, very deep reservoirs and very light oil. So that's why there are a lot of screening guidelines for different EOR methods. This is one example from Exxon in 2010, listing some of the key properties for screening, some of them reservoir, the others fluid properties, and then different EOR method. For example, these are the gas, thermal methods, and then the chemical. Of course, they just looked at polymer and alkali surfactant polymer. And the key properties, the two critical properties really belong to the oil. The API, as we discussed, and the viscosity of the oil. And you see that for gas projects, you need a higher API, lower viscosity. For thermal methods, you can do higher API, lower API and higher viscosities. And polymer and surfactant polymer, they can be somewhere in between, depending on the limitations of the chemicals. And then, of course, there are a lot of other properties, how deep the reservoir is, what is the permeability, pressure, saturation is very important, oil saturation. For EOR methods, you want to have a lot of oil in order to pay for the cost of the EOR project. So if you don't have enough oil and the oil saturation is small, when you start the project, is not going to be economically favorable. Reservoir thickness, you want thinner reservoirs in general for gas, thicker reservoirs for thermal. It doesn't matter for chemical. Salinity of the water is not important for gas or thermal, but is very critical for chemical floods. And temperature impacts the MMP for gas projects and also impacts the chemical flood for selection of the chemicals that are stable under that reservoir temperature. So this is one example. There are a lot of other screening guidelines for EOR tables in the literature. So then I like to look at the simple equation for oil recovery. And that is the amount of oil that you produced is the volumetric sweep efficiency multiplied by displacement sweep efficiency, initial oil saturation per volume, and then the formation volume factor for oil, just to convert the surface to subsurface volumes. So the displacement efficiency is basically telling you the ability of the EOR fluids to remove the remaining oil saturation compared to the initial oil saturation. So that's really the equation, is how much is the remaining oil saturation divided by initial oil, 1 minus that. So that's a displacement sweep efficiency. And this term is how much original oil you have in place. So it's initial oil saturation times per volume divided by B sub O. So if you want to calculate the recovery factor, which is a normalized value of how much oil you produced, this term, divided by how much oil you had initially, then you see that you end up with displacement efficiency times volumetric sweep efficiency. So recovery factor is a function of the two sweep efficiencies. And that's what we're trying to do with implementing EOR methods to improve both of these. In some cases, like for example, if you're doing polymer, you may actually more improve the volumetric than displacement. But in general, we like to improve both of these sweep efficiency to enhance the recovery factor. So a little bit of definition and what are the variables that impact the sweep efficiencies. So this is the displacement efficiency. and basically how much of the remaining oil you be able to displace by your new method. And this efficiency depends on the wettability, surface tension, capillarity, and mobility ratio, which is basically the permeability divided by the viscosity of the displacing and displaced fluids. So you see there are a lot of microscopic properties that would impact the displacement efficiencies. And for example, surfactant, if you add surfactant, it can change the wettability, it reduces the interfacial tension, it reduces the capillarity, and then if you add polymer to it, you're going to improve the mobility ratio. So then you'll be able to improve the displacement efficiency. Same thing with CO2. CO2 can reduce the interfacial tension and reduce the capillarity, especially when it's miscible. And when you add foam, then you're going to improve the mobility ratio. And then we have volumetric sweep efficiency, how much of the volume of the reservoir you were able to contact with your injected fluid. And normally is defined as aerial and vertical sweep efficiencies, but it's very difficult to differentiate the two. So I think it makes more sense to look at volumetric. And this is referred to as more macroscopic effect of the EOR methods, because it depends on the reservoir heterogeneity. For example, if you have layering, the contrast between the layers, the communication between the layers, and then also the permeability variation, both in horizontal and vertical. So how much cross flow you have, that would impact your volumetric sweep. The well pattern and the spacing, the distances between the wells also will impact the sweep efficiency. How continuous your injectors and producers are, or are they disconnected by some sort of shale or other complication of the reservoir. And also mobility ratio. So mobility ratio shows up in both displacement and volumetric sweep. Then I like to discuss, if you haven't heard about incremental oil, this is the way that you can assess the impact of EOR methods as how much additional oil you're going to produce compared to the previous operations. So for example, here, if you look at the oil production rate from the field data as a function of time, for example, maybe point A is the time that we started water flooding. And then your oil production declines to a point B, and this is the time that you want to maybe inject a polymer or a surfactant polymer flood or a CO2 flood. If it's effective, then you see an increase in the oil production rate, and then at some point you see that you reach to some sort of decline again that may not be economic to inject or continue the EOR. So that would be point D. So then you need to know how much additional oil you have produced compared to if you would have continued your water flood. So then you have to do the decline rate analysis for the water flood, which would be like, for example, this dashed curve. And then anything extra here is going to be your incremental oil due to the EOR method. So you don't want to look at the total oil you produce. You have to look at how much additional oil you produce. And that basically tells you the efficiency of your EOR and in terms of the cost analysis as well. So then we have the gas EOR methods. That the gas can be hydrocarbon gas, lean, rich gas, LPG. But a lot of times, most of the countries and operators, they need the gas for other applications and they don't want to re-inject it. So it really depends on where you are and how much gas you're producing. So sometimes it's difficult to use these gases for EOR. But then you have nitrogen, But nitrogen has higher miscibility pressure. So in order to be miscible with oil, you need to have very, very light oil and very deep reservoirs. But it can be good for pressure maintenance, and it can be used for nitrogen foam applications. And there are some nitrogen projects also around the world, very successful nitrogen projects. So this is sort of a picture. This is an older one, but I don't know how much has been changed since then, of among the projects that they use EOR methods, 25% is hydrocarbon gas, 19% nitrogen, 41% thermal methods, and then chemical about 8%, and CO2 7%. And of course, the CO2 projects in the US actually is the highest number of gas EOR projects compared to the rest of the world. So very popular here because of the access to a lot of natural CO2. So then that's why I'm going to spend a little bit more time on CO2, and I know also you guys are interested in CO2 EOR. There are different ways that you can inject CO2. One is just continuously injected, but that's a function of economics and availability of the CO2 gas. You can do water alternating gas. So now you're combining two technologies, water plus gas flooding. And that helps with sometimes increasing the reservoir pressure, become more miscible when you're injecting water. It prevents early CO2 breakthrough and reduces the gravity override that gas usually has. And you can add foam or other mobility control agents in the cycle of water if you want. So it's really versatile and can have a lot of benefits if you do water alternating gas. You can also do huff and puff as stimulation. And as a matter of fact, there are a lot of old projects that they developed the whole field as huff and puff CO2. So you inject CO2, you let it soak, so you shutting the well, you let CO2 contact the oil, and then you produce it back from one well. And you may just repeat this cycle till it gets to a level that you don't produce enough oil. And with this method also, you might store some of the CO2, but in general, most of it is coming back. And then sometimes even for full field, CO2 injection, they may do some huff and puff to start the process, quicker, and maybe move the oil from near the wellbore, improve the injectivity of the CO2, and so on. So that huff and puff can be applied even part of the continuous or water alternating gas injection of CO2. And you have two types of flood for CO2. One is miscible. And that's what everybody's after, because that's where you get the highest recovery potentially. And it's actually not a first contact miscible with the oil. You develop miscibility. So a lot of mass transfer is going to happen between the CO2 and the oil in the reservoir. And you may have a region that is really completely miscible. You can also dissolve CO2 into the oil, and that causes the oil to swell. And that gives a better mobility to oil because it basically increases the volume of the oil. Is like you have higher saturation of the oil. Once you dissolve the CO2 into the oil, you also reduce the viscosity. So now again, you have a better mobility for the oil. CO2 can be immiscible, and you still benefit from injecting CO2 even if it's immiscible, because you will have two phases, and but you still have some solubility of CO2 into the oil, and that causes the swelling and the viscosity effect, and even to some degree reducing the interfacial tension. So there are successful immiscible CO2 floods as well, if you don't have the pressure requirement for miscibility. So why CO2 is such a great solvent? is basically because of its properties. And here I show the PT diagram, pressure temperature diagram. You have the solid, liquid, and vapor region, and this is your triple point, where you have all three phases in equilibrium, and you have a critical point where you have liquid vapor. And normally we say that CO2 is a supercritical fluid at the reservoir conditions, and it basically behaves more like a liquid, but it really still is a gas, but with more of a liquid properties. So CO2 is a great solvent, and it basically have a very good extracting oil ability, and is mainly because of its physical properties. It has a high critical temperature, but a low critical pressure. And as I mentioned, in most oil and gas applications, it's a supercritical liquid and is a great solvent. So many times you see in the literature, they refer to CO2 as a solvent. So it has a high density compared to other gases. So that's why it's more like a fluid. And if you look at the density versus pressure and temperature, the density increases as the pressure increases, and density of CO2 is going to decrease as you increase the temperature, like liquid. So it's really good because then you may have less of the gravity segregation when you're dealing with the oil, but maybe more with the water, but the critical point is with the oil. So it's actually favorable with respect to gravity segregation. The viscosity, CO2 has almost 3 to 4 times more viscosity than other gases. So this is the viscosity in centipoise as a function of pressure and temperature. So again, the viscosity increases as the pressure increases, and the viscosity decreases as the temperature increases, like fluids. So then when you look at the mobility control, you see that it's not as unfavorable as other gases like methane because of its higher viscosities. Then the way you find out if the CO2 is miscible with the oil is through this simple experiment to obtain minimum miscibility pressure. And these are still common type of experiments to estimate the minimum miscibility pressure using the slim tube experiments. So minimum miscibility pressure is the pressure at which the oil recovery levels off at 1.2 pore volumes of CO2 injected in this experiment. So once you inject 1.2 pore volumes of CO2, then you look at your recovery, and when it levels off, that pressure is going to be your minimum miscibility pressure. And minimum miscibility pressure is a function of temperature, pressure, purity of your solvent, molecular weight of the components of the crude oil, the heavy components of the crude oil. So this is one example of showing the recovery at 1.2 hydrocarbon pore volume of CO2 injected as a function of pressure. And then you see at different pressure, they measure the recovery factor, then they increase the pressure, your recovery factor increases, and then you get to a point that it levels off. And then they say this is when it's leveling off the recovery, then this is your minimum miscibility pressure. So pressure at that point is MMP. But again, is a function of a lot of variables. So some of the challenges with CO2 floods, as good as they are, one is the cost of CO2 and availability of CO2. They're also corrosive. So a lot of times you may have to change your infrastructure from your water flood for CO2, so that's additional capital cost. Then you have to separate CO2 from produced gas, because whatever CO2 is going to be produced, you're going to recycle and you re-inject it. to make it more cost effective. There is a compression cost. CO2, you may have fingering that is going to happen, so it's not going to be very efficient in terms of the sweep efficiency, so you may have a lot of fingers and channels. Gravity segregation. So if you have very thick reservoirs, most of the CO2 is going to migrate to the top of the reservoir, and you're not going to be able to benefit from CO2 at the lower part of the reservoir. You may have some asphaltene issues that you have to deal with. And then again, the sweep efficiency is not very good. And you may also have issues with the equipment and the seals in the equipment. So you need to make sure that they are changed for CO2 injection. So I like to just give you a flavor of the recovery factors when you have immiscible CO2 projects, and then some ideas about the utilization, the total cost, and so on. And I believe this was from one of the Department of Energy reports on CO2 projects. So if you look at the recovery factor, this is incremental oil in percent for different field projects, and they were all immiscible CO2. And you see that on average, there is about 8.5% recovery factor, even with immiscible gas. And among these projects, you see that utilization, this is how much gas you need per stock tank barrel of incremental oil, is about 10 on average. And then, of course, you need more for carbonate reservoirs compared to sandstone reservoirs. And then the total cost is, if you include all the operational cost, transportation, and cost of CO2 purchase, is somewhere between $20 to $28 on average, lower for sandstone reservoirs versus carbonates. So still, if the price of oil is $70, it still is pretty reasonable project. It's going to be very economical. Then on the miscible projects, these are statistics on a lot of projects. You see, they give you the number of projects, total data set that they use, and give you an idea about the minimum, maximum, average of the values for the field projects that were flooded with miscible CO2. The key point is looking at the oil gravity. So you see the average of the projects, they had API of about 37. So it's really high API oil and the low viscosity oil. So again, these are good to look at and get some ideas. And if you want to compare your reservoir with these as analogs, it would be pretty useful information. Then we have the some of the Permian Basin. These are in US and Texas, actually, West Texas, that there are a lot of CO2 floods in Permian Basin. The properties of the rock and oil, they're just perfect. And then there are pipelines already in place to deliver flow CO2 from some of the natural storage sites for CO2 to these fields. And these are some of the large projects like Wasson, SACROC, Vacuum East, that they've been doing miscible CO2 floods. And gives you some ideas about the percent OIP, on average about 10%. And then the utilization in terms of the net CO2 to EOR, net is actual CO2 that you purchase, is about 5.6. So again, some good statistics of the performance of these projects in US. Then I like to talk about this project was done by Exxon, and that means CO2. This is a carbonate, a dolomite reservoir, and they did water flooding for 20 years, and then they started CO2 flooding in 1983. Low permeability, and viscosity is about 6 centipoise. So it's one of the most successful CO2 floods in carbonate reservoir. These are some of the early production data. This is actually water flood, is not the primary. So this is prior to CO2 injection. You see it was on a decline, and then this is the decline rate. This is the time they started the CO2, and now you see the increase in the oil production. So this is your incremental oil if you take the area under this curve. At this point, they only injected 18% hydrocarbon pore volume CO2. And the expectation was that ultimately they're going to get about 11% recovery factor. So I just wanted to share some of their conclusions and comments that they made about this field and the process. Exxon did a lot of numerical simulations and of course 3D seismic. And considering this was done in 1980s, they actually had like a 1 million cell simulation model to help them to optimize and manage the flood and the reservoir. Quite a bit of surveillance, especially monitoring the pressure, because that impacts the performance. And then they wanted to re-inject the produced gas, but keeping in mind that the produced gas is not going to be 100% pure CO2, or actually 98% pure CO2, is going to have some impurities that will impact your MMP and is going to increase the MMP. And they were concerned about the MMP because the MMP was estimated to be about 1850 to 2300 psi, and then reservoir pressure was about parting pressure, fracture pressure was about 2700 psi. So they really wanted to make sure that at the same time that they are achieving miscibility, they want to make sure they don't create fractures and the pressure will be below the frac gradient, so less than 2700 psi. They had some issues with asphaltene deposition, so then they used xylene treatment and also monitoring the bottom hole pressure. So a lot of times if you increase the bottom hole pressure, it helps with the asphaltene issues. So again, a very successful project, but that required simulation, modeling, monitoring, and some of the mitigations for example, asphaltene or other issues that they might have had. So this is also give you some ideas about the recovery factor of different fields. The blue is the recovery of primary and secondary for each of these fields. And means is actually is here, the one Exxon did. And the red part is the incremental due to the CO2 EOR. So you see that is not really that great in terms of the recovery factor, at least at the time that they plotted these results. On average, maybe 10% recovery factor after recycling and re-injecting CO2. And that's mainly because of the sweep efficiency. So the definition, if you're not familiar with, for all the EOR methods, you use something called utilization factor, and is defined as how much the EOR fluid you need in order to produce 1 barrel of oil at surface. And usually this is incremental oil. And that gives you a measure of the flood efficiency and also an estimate of the cost of your EOR fluid. So you really don't want to have very high utilization numbers. When they talk about net utilization is whatever, for example, CO2 you purchase. And then gross utilization is total, how much you bought and how much you recycling. So that these are some of the examples of the large CO2 floods. Denver, Means, Rangeley, Seminole. give you the CO2 utility in MCF of CO2 divided by barrel of oil. And the red is what they projected, and the cumulative was actually what they had. And you see that overall about 10, which is a good number for CO2 utilization. So now this is something that can help you for screening reservoirs for CO2 miscible EOR, and most of it actually driven based on actual field projects. If you look at, for example, here, the viscosity versus the gravity, oil gravity of the API, oil gravity, the circles, they're immiscible CO2 projects, and the crosses, they're the miscible. So actually, you can use this graph for highlighting the ranges of viscosity and API for screening miscible CO2 floods. For example, we're saying that API gravity should be greater than 25, ideally 36. And you saw a lot of the actual field projects, they were above 36. Viscosity, ideally less than 1.5 centipoise. The lower the viscosity, the better performance you're going to have. And you need, in terms of oil composition, you want to have high percentage of C5 and C12. That helps also with the miscibility. In terms of the depth of the reservoir, you need to be greater than 2,500 feet for CO2 to be miscible. And you want to make sure that the reservoir pressure is greater than MMP. You don't want very high reservoir temperatures because higher temperature increases MMP. You don't want gas cap. You don't want extreme heterogeneity, like if you have really high permeability channels, teeth zones, or fractures. High oil saturations, ideally greater than 55%. And permeability, it really doesn't matter for gas injection, but in order to complete a project sooner, you need to have good injectivity. So a lot of times we propose something greater than 1 millidarcy. Formation can be carbonate or sandstone. A lot of experiences in US has been with carbonate reservoirs. And it's important where the field is, because you have to be careful that if there is no existing infrastructure and the pipelines and the availability of source of CO2 nearby, you need to spend quite a bit of capital expenses to build that infrastructure. And then in terms of the density and viscosity contrast, that's why we don't have very good sweep efficiency with CO2, because CO2, if you want to look at the ideal case, for example, you want to inject CO2 and form this miscible zone, and then it pushes the oil bank towards the producer. But this is not what happens. Due to the contrast in density, CO2 is going to have the gravity override, so it's going to move up to the top of the reservoir, and you're not going to be able to flood this part. And then due to the viscosity contrast, it has a lower viscosity than the oil, then it's going to finger, and of course, you're going to have channeling also due to the heterogeneity. So it's not going to be a very efficient in terms of sweep efficiency. So what are the methods that we use for improving CO2 sweep? One of the cheapest one is the water alternating gas. So again, you use cycles of water and CO2, and there's quite a bit of optimization as how you want to do that, how many cycles you want to do, how big should be the cycles of CO2 versus water. And there are some challenges with that as well. Because you may have some issues with the injectivity. You need to have a source of water, and then you need to know what to do with the water that you're producing. Are you disposing it, or are you going to re-inject it, and so on. But in general, the oil recovery for CO2 floods is correlated with how much CO2 you inject. And normally in the field, they inject something between 15 to 30%. The higher you inject, of course, you may get better recovery. This is laboratory experiment, but in the reality, the higher you inject, the better recovery, but then it's going to be cost issues. And then in terms of the how you want to do the WAG, for example, if you do a continuous CO2 injection, you inject your 30% hydrocarbon pore volume, and then you switch to water, or sometimes maybe cheaper gases, nitrogen. Or you can do a simple WAG that you do equal pore volumes of CO2 and water, and then you just repeat that. But many times the operators, they don't like to do too many of these WAG cycles. The preferred method is called tapering WAG. So you inject upfront more CO2, and then you add little water, and then start, gradually reducing the pore volume of the CO2, increasing the water. So that is called tapering WAG. But it's critical that initially you inject more CO2. And this is showing some results of the field projects, that the injectivity goes down in some of the projects once you do the water alternating gas. For example, here the base case is the water, all the blue ones, and these are all normalized with respect to the water. So for example, in this field, this is the CO2 injectivity. And then when you do the water, the injectivity of water is much less than the initial water flood. But in some cases, it really doesn't make that much difference. Like for example, this one. Not much of change in the injectivity of water after the cycle of CO2. But that's a concern about loss of injectivity during these WAG cycles. And then there is another benefit of WAG is you can do foaming. So you can add surfactant to the cycle of water here and generate foam in situ. So that's another benefit of doing WAG. So I'm just wrapping up on the gas flooding, that some of the remarks, we've seen more and more that more water alternating gas you do in your projects is going to be beneficial. You want to inject more solvent, especially upfront if you're doing WAG. Understanding the impact of viscous fingering versus channeling due to the reservoir heterogeneity. This is due to the fluid properties. Understanding and importance of reservoir characterization and CO2 performance. Doing IOR, improved oil recovery by using horizontal wells and multilaterals. And understanding the displacement mechanisms. What is happening? Is it interfacial tension effect? Is it the swelling effect? What are the key mechanisms? And then use foam for mobility control. And of course, now there are surfactants that you can dissolve them into CO2, so you don't need really water as a carrier fluid, and water is already in the reservoir. So there are papers and publications on using surfactants into the for CO2 without water. So now I'm going to switch to chemical EOR. And this is a technology that has been really evolving and getting better with time due to innovations and more experiences. There are more hybrid methods that have been developed to help to make the process more efficient in terms of recovery factor and more cost effective. For example, alkali surfactant polymer and alkali co-solvent polymer. Surfactants that you can solubilize them in CO2. combining gas and surfactant, low tension surfactant is a so-called low tension gas or foam. Combining polymer injection with low salinity water. Heating up the water when you're doing chemical flood for heavy oil. Not necessarily steam, but maybe just hot water. Using surfactants or alkali in fractured reservoirs for changing the wettability. And these technologies are going to be adaptable, so you can use them for naturally fractured reservoirs, you can use them for heavy oil, etc. So where can you apply these chemical EOR methods? You need good geology. And normally you can tell if you've done a good water flood, that means you have very good, in terms of the reservoir characterization is good and is favorable for chemical EOR as well. You can also, based on the interval tracer test, you can find out if there are issues between, for the connections between the wells and so on. You need to have high content of oil. So rather than looking at the oil saturation, you really need to look at the net pay times the porosity times the oil saturation. And you want that product to be high, greater than 1, but it's better, ideal is if it's greater than 10. So that means you have lots of oil. You need to apply these methods to reservoirs with permeability at least greater than 10 millidarcy. But the higher it is, the better injectivity you have, the shorter the project is going to be, and you're going to produce oil faster. For oil viscosity, so far our understanding is you can do polymer flood up to about 4,000 centipoise in situ viscosity of the oil. When it goes above that, it's going to be more difficult to just do polymer flood and produce the oil. If you do surfactant polymer, maybe up to 200 centipoise oil is reasonable for field projects. For ASP, if you combine it with hot water, you might be able to go to really high viscosities, 10,000 centipoise. And again, these are just some guidelines, but it really depends on a lot of other conditions of the reservoir. So far, due to the limitation of polymer, if you're doing a process that requires polymer, the reservoir temperature up to 120 degrees C. Again, polymer manufacturers are trying to come up with polymers that they can be stable at higher temperatures, but it's not easy. And reservoir salinities up to about 230,000 ppm TDS. And if you're dealing with much higher salinities, then you may want to do a low salinity water flood, and then the salinity will be reduced in the reservoir, and then you look at surfactant and polymer flood. So when you do polymer flood, normally you need to have the injection wells and a producer, and of course you need a facility to mix the polymer with the water and do all the filtration and testing. But it really needs very little changes to the existing water flood infrastructure. And normally you inject polymer, may not need a pre-flush. And if it's successful in terms of mobility control, then you form the oil bank, and the oil bank is going to move ahead of the polymer. So you see an increase in oil production rate. And then at some point you switch from polymer to water. So what are polymers that we use for EOR? These are long, chain-like, high molecular weight monomers. Basically, they're linking a bunch of monomers together to make it to very large molecular weight, up to 20, 30 million molecular weight. When you add very small concentration of them to water, it will increase the viscosity of water. So that's what you're after. But it also has other properties. it can decrease the permeability of the formation. And that happens because it gets absorbed on the walls of the pores, or sometimes it actually plugs the pore and it doesn't get out. It can change the viscosity with the rate of flow. So it's really a shear thinning fluid. As you increase the velocity, the viscosity goes down, which is really a good property of the polymer for injectivity purpose. So what does polymer do? If you look at it aerially from the top, the reservoir, let's say this is a 5-spot, and you're injecting water, and you see that due to the unfavorable mobility ratio, potentially heterogeneity, you have water that breaks through really early, and you don't get a chance to sweep all the oil. If you add polymer, you increase the viscosity of the water, and that is going to reduce its mobility, so it's going to move slower in the reservoir, and you have a better chance of displacing the oil. So you're going to have much higher sweep efficiency, and you're going to contact more oil. If you look at it in a layered sense, let's say you have a reservoir that has 3 layers of permeability, and this is the one with high perm. Now you're injecting the water, most of it is going to go into the high permeability layers, and you're going to have water breakthrough early on, and then you produce so much water that you're going to shut in that well, even though you have a lot of oil remain behind. Now, if you add polymer, you're going to viscosify the water, and it's going to slow down the movement in the high permeability and creates cross flow. So now, because of the pressure is going to increase in this layer, you're going to have some of the polymer that is going to go into the lower permeability layers, and then you have more fluid also going into those layers. So it looks like almost like you have a piston-like displacement, and more efficiently you're going to displace the oil. So that's what polymer does. So polymer is really considered a complex fluid because it has a lot of properties. It can increase the viscosity of the water. The viscosity changes with the velocity. It also has degradation. So you may lose viscosity due to different degradation mechanisms, including biodegradation, including mechanical degradation. It reduces the mobility of the water. And then also there are some transport properties like injectivity, adsorption, permeability reduction, inaccessible pore volume, and as we talked about, the degradation. So that means like you have to be aware of all of these properties when you're selecting a polymer for a specific field. And you have to do a lot of measurements in the laboratory. So these are some of the variables that polymer is going to be sensitive to. For example, what is the molecular weight of the polymer that you select? What type of polymer you're picking? Is it a biopolymer? Is it a synthetic polymer? Which class of polymers are you choosing? Reservoir temperature, water salinity and hardness in the reservoir, and the water that you're going to use for injection. Water pH, concentration of polymer, shear rate or velocity, reservoir rock mineralogy, and if you have any oxygen, H2S or iron present in the water or in the reservoir. So all of these will may impact your performance of the polymer. And then in terms of laboratory screening, for field implementation, you see this is not even a complete list. These are some of the measurements that you have to do in the lab to select the polymer. Depending on the reservoir temperature, you may have to do long-term thermal stability, making sure it's compatible with your injection water and produced water, and then decide if you want to use an emulsion polymer versus a powder, Do you need any additional protection packages with polymer? What is the injectivity and adsorption and retention? So quite a bit of laboratory experiments are needed in order to select the best polymer for your field. This is, I gave the reference here, 2016, talks about some of the field tests, relatively recent, including some of the ones in Brazil, highlights the concentration of polymer that was used, viscosity of the polymer solution, the oil viscosity at reservoir temperature, endpoint mobility ratio. You see they're all very unfavorable. Anything above 1 is unfavorable mobility ratio. And then how long they injected the polymer, and if they did the tapering or grading. So these are, again, really nice projects if you're looking for analogs and you want to compare your field with some of these that they've done successful polymer projects. I just want to highlight one project, and this is one in Canada, Alberta, Medicine Hat, that they used horizontal wells. They used 5 horizontal injectors in a line drive, and they used this polymer FlowPAM 3330. And it was a pretty successful project. So in terms of looking at the recovery factor, they actually divided up into the ones that they were great performers, average performers, and the ones with some issues. So the one that is a great performer, this is the water injection rate, the blue. The green is if they would have continued water flooding, so the baseline. And the red is the oil production rate. And this is when they started the polymer injection. So you see the increase in the recovery factor at that point. So this was one of the great performers. In one of the other wells, they had issue with the channeling, and they ended up doing a polymer gel conformance. And then after that, it looked good, but then initially they had some issues and they had to shut in the well and so on. The utilization factor for this project was actually pretty good. So for polymer is kilogram of polymer per barrel of incremental oil. And then they look at for each of the patterns, you see that somewhere between 4 to 8 is the utilization factor, which is very good. 4 to 8 kilograms of polymer per barrel of incremental oil. That's the utilization. So this was a good, successful using horizontal wells for heavy oil. Then I like to talk about surfactant floods. Now that we have the polymer, all we need to do is add some surfactant to make it surfactant polymer flooding. And the purpose of surfactant is to reduce oil-water interfacial tension. And of course, you're adding polymer for mobility control because surfactant does not provide mobility control. Surfactant just reduces the interfacial tension and you'll be able to mobilize the residual oil. So this technology requires small well spacing. And of course, since you have to buy most of your chemicals at the beginning, then you need large initial investment. And due to the oil production that is delayed, because you have such a great sweep efficiency with polymer, then you have a low rate of return. But in terms of the actual ultimate recovery factor is one of the highest compared to other EOR methods. Gas flooding or polymer. Typically, this is the sequence of injection. Sometimes you may need to do a pre-flush of specific water, like let's say you do a low salinity water flood as a pre-flush. And then you inject all of your chemicals, surfactant, co-solvent, polymer, whatever salt that you need in one slug. And that's called this chemical slug. You inject that, and then you continue with your polymer. It's called mobility buffer, because you still need to have good mobility control with polymer to be able to push the oil that has been, banking, and also all the surfactant and emulsion that is formed in situ. So we continue injecting polymer even after we stop the surfactant. And these are some of the typical slug size. This is normally 0.1 to 0.5 PB, and we continue with whatever mobility requirement that is needed for polymer. And then there is a lot of customization of surfactants here. And we need to, depending on the application, you may want to have your surfactant more hydrophobic versus hydrophilic. So there are a lot of chemistry of modifying these surfactants to make it favorable for certain conditions. So this is typically the head of the surfactant, which is likes the water, is hydrophilic. And this is the back of the surfactant that is basically carbon chain, and it likes the oil. So you need to balance the water liking and oil liking of the surfactant. These are typical phase behavior experiments that we do to understand the behavior of surfactant as a function of, for example, salinity. And we do the measurements on all of these fluids to know what is the viscosity, what is the interfacial tension, and make sure that everything makes sense for the project that we're going to implement surfactant flood. Based on these test tubes, we construct these solubilization curves. It gives you the solubility of oil and water in the microemulsion phase. And the interesting part about this is by knowing the solubilization, you can actually estimate the interfacial tension. So for example, for this case, the interfacial tension at this point is 10 to the minus 3 dynes per centimeter, ultra low interfacial tension. And that's what you're after with surfactant flood. The end is the effect of interfacial tension reduction and mobilization of residual oil. So what we're trying to do here, we're trying to mobilize the residual oil that we left after the water flood, for example. And the way to do it is by reducing the interfacial tension between oil and the water. And then as a result, this is the residual saturation as a function of capillary number. You see that you're normalizing, you're basically mobilizing the residual oil. It's become less and less as you lower the interfacial tension. So that's how the surfactant or even CO2 miscible floods work. And then once you do this mobilization of oil, then your relative permeabilities are going to change, because now you're producing the residual oil and your relative permeability to water should be enhanced. So that's another benefit of surfactant flooding. You mobilize the residual oil, and then at the same time, your relative permeability to both oil and water is going to increase. And that's also very favorable for mobility of the fluids. So how are we doing time-wise, Luis?
I'm sure we are already past a little time, but things are so good that I didn't want to interrupt you. So,
but, because I had a plan that if the time doesn't permit, I would just stop at the end of the chemical, and I won't be able to cover the thermal. I have just, few slides on thermal, so my focus was really on gas and chemical.
Sounds great.
I believe we don't have any other lectures for today, so if you want to keep going, we would thank you a lot. It's up to you.
No, I'd be happy to. I just want to make sure that it's okay with you guys.
Yeah, it's okay. We will be happy to listen as well.
Okay. All right. Perfect. All right. So then again, this is the effect of surfactant on relative permeability. This is water, oil, and now this is the surfactant flood and enhancement in the relative perms. Then you've seen I mentioned alkali, and there are a lot of now publications on using alkali as alkali surfactant polymer. And why do we need alkali? Alkali is actually used for heavier oil, because once you have this low API oil, they have some acidic components in the oil that if you raise the pH by adding alkali, you're going to generate some natural surfactants, soap. So sort of like, for just adding cheap alkali, you're going to produce expensive surfactant in situ. And that surfactant also reduces interfacial tension. It reduces the viscosity of the microemulsion. And in general, a high pH phase behavior is much better than a low pH. The samples, they equilibrate much faster compared to a high pH formulation. And there is always a synergy between the surfactant that you choose, that a lot of times is anionic surfactant, and the soap that you generate. So you want to make sure that the synergy is there, and then once they move together, you're going to get really nice results, and it's going to be much more cost effective than surfactant polymer flood, because alkali is cheap and you don't need to inject as much surfactant. You rely on the soap generation. So this is how actually the process is done for ASP or even ACP, replacing surfactant to co-solvent. So some of these oil, they have acids that depends on the type of crude oil. And the number of acid groups that you have is normally characterized by acid number. And acid number is defined as the quantity of the base, normally potassium hydroxide, that you use per gram of oil sample to neutralize the acid in the oil. So a lot of times, part of your oil composition measurements, they give you the acid number or total acid number, TAN number. And based on that, you know if it's going to be an active oil or not. The process is very similar to surfactant polymer. You inject ASP slug, and then you follow by more polymer for mobility control. And you form this emulsion, and is also the oil bank, because you're mobilizing the residual oil, and the residual oil that is mobilized is going to move ahead of your emulsion. So always oil is going to be produced first, and then you follow by some emulsion and some of your polymer. So that's how it works. Nothing significant about the injection of these chemicals. So I'm going to mention one project because the formulation was developed at the University of Texas by Professor Pope and his colleagues. And this field was an ASP, but the oil wasn't active, but still they injected alkali to reduce the surfactant absorption. So this was an 11 centipoise oil, reservoir temperature 80 degrees Fahrenheit, and the distance between injector and producer about 230 feet. So it was a 6 5-spot patterns. So again, the distances between injector producer is about 230 feet. And of course, this is not a confined pattern because you are actually going to inject more chemicals than is needed. And not necessarily all the production is going to be from your chemicals. So they produced quite a bit of oil, but not as much as we expected. And the problem was, if you read the paper, that they did not have confinement in the lower 3 patterns, and a lot of the chemical got lost to outside the pattern. So after some times, they stopped injecting the chemicals here, and they focus more on the upper patterns. So again, this is how the pattern is, and they added some additional wells for confinement purposes, but it really didn't help him. So like this is one well here, there is another well there, one well here, mainly for confinement, but it wasn't as effective as they expected. And then this is how quickly they were very ambitious to move really fast from developing a formulation to actually going to the field and try this process. So of course they did a single well tracer test to get some ideas about the residual oil, which was about 28%. Then they drilled new wells, stimulated the wells. They had a pre-flush, and then they did another tracer test to get the residual oil for the ASP formulation, and they saw that it dropped from 28% to 8%. So the recipe of ASP was very successful in reducing the residual oil. Then they did interval tracer test, 12 unique tracers in each of the injectors to make sure that the wells, they're connected and there are no surprises there. Then they injected the ASP. And in December of 2010, they started the polymer drive. So you see from end of 2009, they already in 1 year, they were doing the polymer drive injection. So very quickly they did this pilot. And this is the results that was published. This is the average oil production from this scale. So from less than 20, they were able to increase it to about 80, 70 barrels per day. And this is the total liquid production. And this is the injection. So overall, they were very happy. And they were ready to extend to much larger scale project, but then the company that had this asset, they changed their direction and they focused more on shale and tight oil. So some of the limitation with ASP or SP, permeability below 10 millidarcy is going to be difficult for polymer injection and then also the longer project life. Polymers may not be stable for long times above 220 degrees Fahrenheit. As I mentioned, there is a more expensive polymer that you can go up to 120 degree centigrade, but they're more expensive. You want crude oil viscosity to be below 100 centipoise for SP, but it can go to higher with ASP because of emulsification with alkali and reducing the oil viscosity. And pore sweep efficiency in extremely heterogeneous reservoir, like if it's a fractured or you have very, lot of shale barriers, and normally you leave the oil saturation in the lowest permeability rocks. There are limited experiences with carbonates and fractured reservoirs. And you need smaller well spacing if you're staying with vertical wells, or you need horizontal wells. And actually the EOR, the horizontal well technology and multilateral has been really helping. And you've seen some of the projects with polymer flood with horizontal wells that you can inject at much higher rates and you have more contact with the oil with horizontal wells. So on the concluding remarks on chemical EOR, low salinity polymer flood has great potential in reducing the polymer cost and extending the applicability of conventional polymers to higher temperature and salinity reservoirs. So once you reduce the salinity, you might be able to use cheaper polymers that they're stable at that salinity and temperature. So we've been really pushing for this hybrid method of low cell and polymer. Hybrid processes should get more attention. For example, combining low tension surfactant and gas, or chemical and thermal methods like hot water or electrical, heating. Both polymers and surfactants have improved and are applicable to harsher conditions. So you really need to look at the new chemicals that are coming into the market with higher efficiencies and even a lower cost in some cases. Chemical EOR is complex and requiring a high level of expertise to implement. But one of its greatest advantage is its versatility, flexibility, and synergism with other EOR methods. So we always say, yes, chemical EOR is complex, and you really need to have experts and people that they're familiar with the technologies, not only in the laboratory, but also in the field, and also doing numerical simulations. But then you might get, really good response in terms of recovery factor with polymer and alkali surfactant polymer, for example. So do you want me to continue, or it's entirely up to you?
Yes, please, go on.
Okay. So now the last class is thermal recovery processes. And we talked about steam drive, cycling steam stimulation, huff and puff, SAGD, which is the two horizontal wells, and is basically based on gravity drainage, combustion, and then various enhancements. And I'm just giving you some typical recovery factor ranges for these methods. For example, steam drive is 50 to 65% OIP, and then the utilization is half a barrel per incremental barrel. And if you do huff and puff, of course, you need more steam, for example. So in terms of recovery factor, of course, you're getting much higher recovery, but the reason is because you have so much oil initially in the reservoir. It's almost like no primary is done. So how does this technology work? Is really, there are a lot of other mechanisms happening during these steam floods or in situ combustion, but number one is the reduction in the oil viscosity when you add the heat to the reservoir. So this is one graph of showing viscosity in centipoise as a function of the reservoir temperature, the oil at reservoir temperature. And these are different oil from Canada, and the fields also given. So the key is you may start with here like 10 million centipoise, and then by increasing the temperature, you can get to really low viscosities. So that's how it works. So in every cycle of 100 degrees C, you see significant drop in the viscosity. And keep that in mind, this is on a log scale. So that's how thermal methods work, lowering the viscosity of the oil, make it more mobile. So steam flooding, or they call it steam drive, you need to inject continuously steam at 80% quality to displace the crude oil toward producing wells. Actually, now there are new technologies that you can have steam to almost 90-95% quality. So then that means like the heat losses is not going to be as crucial as it is with 80% quality steam. Normal practice is to start with the huff and puff for the producing wells, so sort of helps speed up the process of production and sometimes even injection. Oil recovery mechanisms, heating the oil and reducing the viscosity. supplying the pressure to drive oil to the producing well, because as you add steam, is like gas, and so you're basically pushing the oil towards the producer. Some distillation of steam happens, especially with lighter crude oils. And then one improved technology is SAGD, that in some reservoirs actually is going to be more efficient than steam flooding, conventional steam flooding. So these are different techniques for steam flooding. One is if you do huff and puff. So again, is a one well, but you can develop the entire field with all of these wells that you can do huff and puff. You inject the steam for maybe days or week, and then you shut in the well, let the steam contact the oil, lower the viscosity, and then you produce back from the same well. And then once the oil production goes down, you may want to repeat that cycle. So that's huff and puff. Or you need to have injector producers in a pattern with the vertical wells, and then you continuously inject steam. Or if it gets to a point that you're not producing as much steam, then you may push it with the gas, for example. And then the water that you produce is going to be separated and then treated and used in the steam generator. So they're very concerned about the water usage for steam floods in a lot of places, and so they have to separate the water and then reuse it for steam boilers. The SAGD, number of projects done, successful ones in Canada, and now you see more and more other places that following the steam-assisted gravity drainage. So this is involving two horizontal wells. Producer is at the bottom and injector is at the top, and you inject steam here, and then due to the gravity drainage and by conduction of the heat, the oil is going to drain, and then you're going to capture it with the bottom producers. So this is called the steam chamber. And there are concerns about how far these wells they are, and then you're going to have multiple of these pairs of injector producer to develop the entire field. And then there are a lot of optimization in terms of how far these pairs of wells they can be. So it's a complex process. So with respect to the continuous injection versus huff and puff, normally for huff and puff, you may inject for anywhere from 2 to 30 days. Then you soak for maybe up to 30 days, and then you produce 1 to 6 months. So that's normally the cycles. And when you do steam drive, of course, you're going to inject it continuously from your injector well. This is the steam-assisted gravity drainage, SAGD. And the production is dominated by gravity drainage. And there are a lot of commercial and pilot projects in Canada using this technology, SAGD. It's very important what is the thickness, oil saturation, porosity, vertical permeability, and if there are shale layers. Because this is all about drainage. You should be able to drain the oil from higher layers to the producer where it is at the bottom. So if you don't have good vertical permeability, you're not going to have good drainage. So it really needs very special reservoirs, relatively homogeneous. And when you inject the steam, it's going to, because of its lower density, is going to move up, and then it's going to drain due to the drainage and form this steam chamber, so-called. And initially, the steam chamber is small, but as you inject more and more steam, the chamber, it gets bigger. But then it reaches to a point that is not as effective anymore and is going to hit the cap rock. So then that's probably the end of the project. Normally, the wells, the horizontal wells, they can be anywhere from 90 to 600 meter, and the offset between the injector and producer 4 to 7 meters. So they're not very far apart, the injector producer. Well, this is at the depths. Sorry, this is, and then it can be about 1 kilometer long, each of the wells. Normally, they drill the producer first. And they want it to be as close as possible to the bottom of the reservoir so they don't miss much of the oil. And then they drill the injector. And many times also they do startup. They may do some huff and puff in both wells, injector and producer, again, to reduce the viscosity of the oil, and they may just circulate the steam. And then the SAGD can continue for many years. You just continue injecting till it gets to a point that you're not producing as much oil. So how do you define the performance of SAGD, or in general steam floods, is the steam oil ratio, SOR. And that is the volume of the steam that you need to produce a certain amount of oil. It does not talk about the energy efficiency. You never talk about, how much, for example, fuel you need to use to generate steam. It's all about how much steam is used and how much oil is produced. And the purpose is to minimize the SOR. So you want to minimize the amount of steam that you use to generate the produced oil. Good performances range between 2 and 3.5 for steam oil ratio. And some of the bitumen production rate and recovery factors, because with SAGD you can go to very extreme viscosities, is anywhere from 400 to 1,000 barrels per day per well pair, and recovery factor might be greater than 50%. So very, very efficient process. So one of the key issues with thermal methods, steam flood, is the heat losses. And the successful projects are the ones that you can manage the heat loss, because you're spending the money to generate the steam, and steam is what is going to cause the recovery. And then if you lose that energy, then it's not going to be very effective. So there are different sources of heat losses. Surface, like, you want to have insulated lines and equipment, minimizing distance from the steam generator, the boilers, to the wellhead. And that's usually the smallest source of loss, because they're really good in terms of making sure they have insulation and so on. There are a lot of also water issues with steam flood projects, because you need a fresh water source for boiler. Otherwise, it's going to cause scaling. Then you have to do chemical treatments, and that one of the reasons that they don't want to go above 80% quality steam is just basically a long-term usage of the boilers. And they need quite a bit of purification at the surface when the water is produced. So either they dispose it or they use it for the boiler. So that's additional cost. Major loss of heat is actually due to the loss to the rock and water. And that's why you don't want to do steam flood for reservoirs with low porosity. So the rule of thumb is you want porosity greater than 30%. You don't want to do steam flood for reservoirs with high water saturation. So that's why you don't want to do water flood and then do steam flood, because it's going to be very inefficient. A lot of heat is going to go into the water. And then you need to have high oil saturation times porosity. So that's your oil content. Rule of thumb is oil saturation times porosity be greater than 30%. And hot water flood is not very efficient compared to steam because you have additional energy, latent heat with the steam that you don't have with hot water. So for very viscous oil, normally steam is preferred over hot water. So how do you control the wellbore heat losses? If you inject fast, you have less heat losses. If you can generate steam downhole, then you don't need to worry about heat losses from the surface to the bottom of the reservoir. And that's why a lot of times you cannot do a steam flood for very deep reservoirs because of the downhole, these losses in the wellbore. You need to vacuum the annulus and do insulating the tubing. If you do that, you might be able to go to deeper reservoirs. For example, if you don't insulate the tubing, then your formation should not be greater than 1,500 feet for a steam flood. But if you insulate it, you might be able to go to much deeper. Or you want to do in situ combustion. So if a reservoir is very deep and you're concerned about heat losses, then in situ combustion or high pressure air injection might be the way to go. This is a summary statistics of some of the California steam drive. There are a lot of heavy oil in California. They've been doing steam flood for many years, and now they're cutting back due to the environmental impact of steam, due to the carbon footprint and also the usage of the water. But these are some of the large fields. You see on average, the API is about 14 of the oil. Reservoir, they're not very deep. Wells, they're very close to each other. These are all vertical wells, 1.5 acreage. And then talks about steam oil ratio of about 4. So this is considered reasonable, cost effective. So that gives you some ideas about some of the projects in US. This is one of the largest projects Chevron has been doing, Kern River. And initially they started with 7 spot patterns, but then they extended the field, with 5 spots and so on, and brought the spacing closer. The reservoir, the viscosity of oil at reservoir temperature is about 3,000 centipoise. And when you heat it up to 350 degree Fahrenheit, it drops to 4 centipoise. And average oil saturation was 52% and residual oil saturation 33%. So they did a steam drive, and it was about 7 years of steam injection. And they produce about 3 million barrels of oil. And cumulative oil steam ratio was 0.16, or steam oil ratio of 6, a little bit on the high side, but 37% recovery. So it was very successful for almost 3,000 centipoise oil. And these are some of the results of early 1975, and you can find, their later performances in the literature. But this is the oil production rate increase. And this is the cumulative water-oil ratio. And this is the steam-oil ratio. So reasonable, about 6. So again, very successful. There are many, many examples of successful steam floods, not only in the US, around the world. But again, today, they're minimizing the number of steam projects, both in Canada and in US, due to the environmental impacts. So some of the concluding remark on heavy oil. There are a lot of oil, trillions of barrels of bitumen in Canada and Venezuela. and these are going to be important source of energy. Everybody believes that steam needs to be phased out because of the high natural gas cost and the CO2 emission. And development of cost-effective non-thermal methods is the key technical challenge. And of course, you've seen some people, they're looking at solvent. They're looking at CO2 also for heavier oil. May not be as effective as light oil, but they're using it and they can get credit for CO2 storage. So finding ways to reduce the viscosity of bitumen and also understanding the impact of geomechanics of unconsolidated sand is going to be, again, a major technical challenge that need to be solved. But it's such huge scale in terms of reserve that a successful heavy oil recovery project requires a large capital investment and a well-designed project management by well-trained technical team. So again, it's not easy, and we need to think about different ways of producing these reserves, not necessarily with steam. So that's, I think, all I have to say. And then I just want to finish my talk with showing you the graph that I showed at the beginning of the ways to maximize the recovery. And just going back to our discussion, for example, to produce the residual oil, you may want to do miscible gas, surfactant polymer, alkali surfactant polymer flooding for lighter oil. If you have high viscosity oil, then in order to get a better recovery, maybe you want to do steam flooding, polymer injection, ASP, ACP. If you have heterogeneity in the reservoir, polymer helps with the conformance. You can do polymer gel and also foam. So these are all some chemicals that can help you with maybe blocking the high permeability layers and then diverting the flow, so they can be used as diversion. And for the fractured reservoirs, that matrix is oil wet, using surfactant for wettability alteration might be a way to go. And there are a lot of laboratory work that has been looking at the imbibition and enhancing imbibition of surfactant and water into the matrix by altering the wettability. So these are some of the methods that a part of EOR will help us to maximize the recovery from reservoirs with different properties. So I'll be happy to answer questions if there are any. Let me see if I can I hear you guys when you ask questions now?
Yes, I believe if you want to stop the sharing your screen so you can be in the platform with us.
Okay.
I can remove. Okay, so you can go back to
here.
Yeah, to StreamYard. Yeah.
Okay.
Okay, so thank you very much for your excellent presentation as usual. It's always a pleasure to hear you. There are quite a few questions here. We'll read some of them. So the first one from Ana Julia Silva, she asks you, are the costs of hybrid EOR too much higher when compared with single EOR?
No, actually, sometimes it might be even cheaper. For example, one example is if you're doing, for example, low salinity polymer flood. If you have very high salinity water, then you have to use a lot of polymer, and it's going to be, and then you may have to use more expensive polymers per pound. But then if you have access to low salinity water, then if you use that low salinity water, your requirement for polymer is going to go down. In addition to potentially, you may get some additional recovery due to the low salinity. Okay, so not necessarily they're more expensive. Actually, they can be more cost effective.
Thank you. A question from Tainara. Besides USA, where the hybrid EOR have been applied?
Well, actually, we don't have that many of them applied yet. But like, for example, foam is being used in some of the pilot projects in US with CO2. And they're also looking at it in the Middle East, like, UAE, Abu Dhabi, ADNOC, also in Kuwait. They're looking at some of this hybrid CO2 foam or gas and low tension surfactant. So they're in the development, not necessarily they've been actually used in the field yet.
Okay, another one from João Vitor. Is a hybrid EOR injected in the same well bore, or is it necessary to inject wells for each EOR method?
No, it's the same. It's the same well. So like if you're doing CO2, for example, CO2 and chemical, you may just inject the water with the surfactant for a period of time in the injection well, and then you follow by CO2. Or by nitrogen to generate foam. So it's the same well. You don't need to have multiple wells.
Okay, another from Rafaela. The CO2 costs could be reduced putting together the carbon capture and storage methods?
Yes. Well, carbon capture cost, that's what they're working on right now, because that's the huge cost of capture and purification of CO2. And there are a lot of groups that they're trying to bring the cost down on the capture side. But then for the CO2 storage, if there are policies that are going to be finalized, that if you store CO2, you get credit for storage of CO2, then you might be able to combine it with EOR CO2. So then you produce oil, and then you also store some of the CO2, so-called carbon capture storage utilization. Yes, that would help, but I'm not sure that will impact the cost of capture unless we come up with a new technology for capture.
Thanks. Question now from Emaline. Dear Mojdeh Delshad, thank you very much for your lecture. I would like to know if there is a basic difference between CO2 when you use it for EOR and for storage purpose.
Not really. It's really the same CO2. The key is for the CO2 storage, which we also use for EOR, it has to be relatively pure, like 99% pure CO2, especially for storage in the aquifer. But in terms of the actual process, there is no difference. No difference.
Okay, a question from Igor. The more miscible is the CO2 with the oil in a given formation, the best is the recovery achieved. Is this the main factor?
Yes. So if you have a miscibility for a longer time in the reservoir with the oil, that's going to cause the mobilization of the residual oil, because again, like surfactant is going to increase the capillary number and reduce the residual oil. But even if you don't get miscibility for entire injector producer distance, even for a limited time, miscibility and being immiscible is going to be still effective, because even if you don't have immiscible CO2, you're going to have some solubilization of CO2 into the water, and that is going to cause swelling, is going to give you some interfacial tension reduction. But of course, if immiscible is basically completely mixed with the oil, that's perfect, but it may not happen.
Thank you. A question from Sandra. Actually, Sandra had asked a question before, and she said that it has already been answered, but she still asks about the applicability of biopolymers, which one we usually use in the industry.
Okay, so biopolymer, I didn't include biopolymer because it will be a long lecture on polymer. Biopolymers, they've been used actually in the past significantly. Xanthan gum is the most common biopolymer that was used in a lot of pilots in the past. But then there are improved versions of biopolymers, and there are two main companies. One is BASF Wintershall, the German company, and the other one is Cargill, that they improved biopolymers. One of them is the schizophalan from Wintershall, and the other one is scleroglucan from Cargill. And they really improved the properties compared to xanthan gum. Higher stability to temperature, and then and also viscosifying power. And I did quite a bit of testing of the biopolymers, but then I'm not sure we're ready to respond to the biodegradation, because it requires a really very careful testing on the field site, not in the laboratory, on finding the right biocide that would kill the bacteria so it wouldn't attack the biopolymers. So that's one issue, the biocide selection. And the other one is the permeability. It seems like these polymers, they're really good for very high permeability reservoirs and high temperature. When you go to maybe 200 millidarcy permeability, they don't flow very well because of their rigid structure. So that's why there are really not that much today application of biopolymers, with the exception of BASF did a pilot in Germany using schizophalan. You don't see any more applications of them, unfortunately.
Yeah, I agree. Another question from Jessica Fernandes. You talked about acid number. What about base number? What's the connection between acid? Actually, is there any influence from the base number on alkaline?
No, normally for acid number and base number, we look at it for low salinity water or smart water. But for alkali surfactant polymer, all we care about is the components in the oil that have acidity. And actually, even that is not really the right way of quantifying the reactivity of the oil. So we just look at those components that they can be converted to surfactant when you raise pH. So base number is not relevant for the alkali application, but it does for the low salinity water.
Yes. And finally, from Igor again, the steam method has ever been applied in an offshore field?
Good question. I think I have to look at my references. I believe that I saw somewhere that there has been a steam flood offshore. You don't hear that many of them because of the steam generation and some of the safety issues potentially with steam. But I think I've heard that there might be one. I need to look for it, and I can send it to you, Luis.
Okay.
Right? Yeah.
Thanks.
Not that many. Not that many.
Yeah. I have one question myself.
Sure.
When you compare offshore with onshore, especially for chemicals, the main issues are logistics and space on platforms. But there are a difference, actually technical difference, not logistical or this kind of problems. I mean, from reservoir point of view, there are no difference if you are offshore or onshore, right?
That's true. And then also the well spacing.
Oh yeah, that's right.
So that's the biggest issue.
Uh-huh.
And that's why the only projects they've looked at offshore, they're polymer floods with horizontal wells, because now you have more the wells are so long that you can inject so much polymer. And then there is one offshore surfactant polymer flood Bohai Bay in China.
Yeah.
And Chevron in Captain Field offshore, UK, they were planning to do alkali surfactant polymer after their polymer flood with horizontal wells. But I don't know the new company that took over the field, the Captain Field, if they're still going to do the surfactant or they're just going to stay with polymer.
Mm-hmm.
So you don't see that many surfactant, alkali surfactant polymer offshore, mainly because of the space, logistics, and well spacing.
Mm-hmm. Yeah. Okay, thank you. So no more questions. Thank you very much again for your time and for your incredible presentation. I would like to return to SPE.
Okay. First of all, I want to apologize for any technical issue you had at the beginning of the lecture. Unfortunately, those problems can happen in an online event. And also, I want to thank you so much, Dr. Delshad, for accepting our invitation. We are really, really honored to have you in our event. And I also want to thank you, Dr. Lamas, for helping us and supporting us in this event. And also I need to thank you our sponsors, that Repsol, Sinopec Brazil, and Baker Hughes, and also our support E3S. I also would like to thank all the officers and SP UDESC involvers that make put so much effort for this event happen. And I need to say some further informations. Our event tomorrow is keep going, so we have one main course and 2 more lectures. The main course will happen during the afternoon, and the lectures during the night. And another important reminder is about the campaign for Amor para Down Association. It will be available through the event. Make your donation. Thank you so much, both of you. Now I'm going to say all of these in Portuguese. So, muito obrigada, professor Lamas, professora Delshad. Eu queria estender nossos agradecimentos aos nossos patrocinadores prêmio, Repsol, Sinopec Brasil e Baker Hughes, e também a empresa apoiadora E3S. Eu também queria agradecer ao UDESC e a todos os officers do capítulo que fizeram esse evento acontecer. Também lembrar sobre a doação para a Associação Amor para Down, esse QR Code aí que está aí na tela, faça sua doação. E para amanhã a gente vai ter mais 2 palestras e um mini curso. Nosso mini curso vai ser sobre workshop em supply chain. Não percam, e também vamos ter 2 palestras. É isso, todas as informações dentro do nosso site. Para informações rápidas, temos o chat ao vivo lá, e a gente responde o mais rápido que puder. Então, eu acho que é isso. Tenha uma boa noite. Muito obrigada.
Thank you so much, Dr. Lamas. Thank you so much for organizing everything and your invitation. It was my pleasure.
It's our pleasure to have you.
Thank you. Bye-bye, everyone.
Bye-bye.